Mm. So, good evening, students. So, today we will started our tutorial 9 class. Okay. So, tutorial 9. So, for today's tutorial, most of the problem we'll be discussing on like different types of statistics where we will be using like for different types of systems of like there are mainly three types of statistics are there. One is for classical particles, that is the Maxwell-Boltzmann statistics. One is for bosonic particle, that is boson statistic, and third one is for like for particles like for which fermionic particle, that is for the Fermi-Dirac statistics. Okay. So the problem that we will be discussing will be mostly based on these three types of statistics. Okay, so we are mostly discussing three types of statistics. One is the Maxwell-Boltzmann statistics. Second one is Boltzmann statistics. Third one is Fermi Dirac statistics. This we can use the short term of this, which is MB stat. This is B stat. This is FD stat. Okay. So these are the short terms that we will be using during solving the problems. Okay. So let me check the recordings. So maybe the problem should focus on these three statistics. Okay. So now, so let's start from the question number 1. So question number 1, what it is going to teach us? Question number 1 is consider a very simple gas of identical particles. Suppose that each particle give possible quantum states. what will be the probability of having both particles in the same state, in the same state. So this is the problem. Okay. So consider a very simple gas of two identical particles. Suppose that each particle can be in one of the three possible quantum states. Three quantum states are there, so each particle can be this one, this one, or this one. What will be the probability of having both the particles in the same state only? So like particles, two particles can have different combination between these three states. Like each combination will have some probability, right? So out of all of this combination, what is the probability of the combination of that particular combination where both the particles will share the same state? Okay, that means it will be either like this or like this or like this. Like both the particle cannot share state, right? So before solving this problem, uh, let me just something. So, um, so here actually one crucial thing I missed. So here, but in the problem it says that in case of FD star, okay. So in case of, so that means these particles are basically fermionic particles, right? So that's why it basically obeys the Fermi-Dirac. FD means the Fermi-Dirac statistics, right? So if we consider those particles as fermionic particles, then what will be the probability that each particle, both the particle will be share the same states? Okay. So before solving this problem, what I will do, that just write, just like recall all the like properties of these three types of statistics. Okay. So what first comes as the Maxwell-Boltzmann statistics? MB statistics. Okay. So we know MB statistics is mostly applicable for classical particles. Classical particles means they are distinguishable particles, not quantum particles. Okay. So and one other thing is like this, in this case, in classical particles, there is no restriction, right? So like more than one part, like any numbers of particles can share a same energy level. Okay, so that is also a feature, okay, of classical particles. And this like the statistics of this kind of particles has follow a certain exponential distribution function. That also I will write one second. So so first property is classical particles. That means distinguishable. Okay. Second property is no restriction on the number of particles that can occupy a single state. So distribution function. So the distribution function would be, I mean, obeyed by this particle would be A e to the power E by ABT. That E is the, basically E is the energy. This is at a temperature T. So this basically gives us the PD, the PD means power distribution of particle at energy level E at a temperature T. Okay. So that distribution is given by this AC function. This is basically known as the Maxwell-Boltzmann distribution. Okay. This is the NB distribution. Okay. So this is the property of the Maxwell-Boltzmann statistic. That's the NB step. Next comes the Bose-Einstein statistics. Okay. So second one is the Bose, or I can write it B statistics. Statistics. Okay. So here also, like unlike the first case, that is the ND stat, for B stat it's only applicable for bosonic particles. Okay. So what is a bosonic particle? Bosonic particles means the particle has integer value of spins. Okay, like +1, +2, +3, +4, like that. So each particle should have integer value of spin. Okay, that is one of the like main features of a bosonic particles, and these are basically the quantum particles. Okay, so these particles generally are identical to each other. So that means these are not like indistinguishable. You cannot distinguish between them. And here also, one energy state can be occupied by multiple particles. Multiple means more than 2-3 particles. Like you can select several amounts of particles can occupy the same energy state. Okay. So that means that there is basically no Pauli's exclusion principle will be applicable for these types of statistics. I mean, the particles that obeys these statistics. Okay. So these are the three key features of the B stat, and also just like MD stat, for B stat also there will be a particular distribution function that can be obeyed by the particles. I mean the bosonic particles. So let me first write out all the features. So first feature is applicable for bosonic particles. Bosonic means particles with integer spin value. Okay. So second feature is particles are distinguishable. That means basically cannot distinguish them, and multi particles can occupy the same quantum states. That means no exclusion principle. So, and So as I have told earlier, so Pare's exclusion principle will not be applicable for this kind of bosonic particles. And the third feature is the distribution function. So here the distribution function is AP is equal to 1 by e to the power P by, so sorry, P by mu E minus mu. So mu is basically uh, the chemical potential of mu minus 1. So here also is the energy. Mu is the chemical potential. T is the temperature. That is the distribution follows. So these are the three types of statistics. So this is, I hope all of you understood. This type, this type, and lastly there is this type. Fermi Dirac statistics. Okay. So here what happens? So these Fermi-Dirac statistics also been obeyed for by the quantum particles, but here the main difference is the particles now are fermions, not bosons. Okay. So fermions means they are basically indistinguishable, like same, this is same property. But now there is a constraint here, which suggests that no two particles can occupy the same quantum state. So that is not the thing that happens in the previous case, right? So here basically Pauli's particles basically obeys the Pauli's exclusion principle. So because of that, uh, like more than one particle cannot occupy, like if two particles share cannot basically share the same, all the four same quantum numbers. Okay. Which is basically the Pauli's exclusion principle. So let me write it. So this, and fermions basically means like bosons are the particles that have integer value of spin, but for fermions they have half integer spin values. Okay, half, like half plus half, or 3 by 2, 5 by 2, like this kind of values. Okay, so fermions particles with integer spin. Second feature is here also particles are indistinguishable, and no two particles can occupy the same energy state. Okay. So I hope all of you understood. Okay, and here also there is a distribution function. The probability of a particle that occupying the energy level E with the probability, that is Fe, which is R minus by ABT. plus 1. Previously it was minus 1, but for Fermi-Dirac distribution it is plus 1. Okay, so that is the difference. Okay, these are the distribution function. So these are the main three types of statistics, and we have also discussed the properties of all these three types of statistics. Now, what we can do, now we will jump back to our main problem, which basically says that consider a very simple gas of cylindrical particle. Suppose that each particle can have three possible energy condensation. In case of every statistic, what will the probability of having both the particle in the same state? Okay. So, as I have discussed, so as they are obeying the Fermi-Dirac statistics, right? So obeys empty stats. That means they are fermions, right? So this means these particles follow the Pauli's exclusion principle. Exclusion principle. Okay. And if indirectly says that two identical fermions are not occupied the same energy state. Okay. So this means that the question is what will the probability of having both the particles state. So that means that if not more than one particle is allowed to state in the same state, this means for this problem the probability will be simply 0, right? So this means because this statistic doesn't allow us this thing, right? Okay, so I hope all of you understood how to solve this problem. Okay, so now basically in the problem itself it's already mentioned that it's always Fermi-Dirac statistics, right? So which actually indirectly gives you the answer. So if the particle obeys Fermi-Dirac statistics, so that means it obeys also the Pauli's exclusion principle, which basically tells that no two fermionic particles cannot have the same energy levels, or cannot share the four exactly same quantum numbers. So which basically indirectly tells us that the probability of having sharing the same energy state for two fermionic particles will be simply 0. Okay. So this is the question 1. Now we go to the question number 2. So question 2, what is tells question 2? Question 2 basically tells us for the mean function if p equal to 1 by to the power e minus f by dt plus 1 gives the probability of gives the probability of occupation of electron per energy state. This occupation number is nothing but the probability distribution, right? Occupation and probability is kind of same synonymous words, right? So is a probability of occupation of per energy state. Then the probability of equal to f is option 1, option 2 0, option 3 final, and option 4 half. So question is, so that means Fermi function. Fermi function electrons are basically fermions. That's why it's always the Fermi function. Fermi function if gives a probability of occupation of electron per energy state, and if the formula is given, now I have to calculate the probability number of electrons at an absolute temperature t equal to 0 Kelvin when equal to F. Okay. So now, this is the basically. See, probability of state E at a temperature T for fermions is if E equal to 1 by 3 into minus L by AB3 minus plus 1. These are the basically the occupational energy. ये भी Fermi energy. F is the Fermi energy here. Fermi energy. Okay. So so if you solve this function, if t equal to 0 Kelvin, now when E is greater than, so let's E is greater than here, then F will be greater than F means sorry, first E is smaller than E, sorry. So for this case, for t equal to 0, so this term will goes close to 0, right? Because E is less than, so KBT is 1 by 0, so E is less than E by minus F, that means this power term will be negative, so that means 1, this should gives you, so 1 by E to the power something, and that something is nothing by infinity, so this will gives you 1 by e to the power infinity, that means it gives you 1 by infinite, that is nothing but 0, right? So that means 1 by 1 would be coming, this gives you 1. Now next case, case 2, where E is greater than E. Now for the case of E is greater than E, then Fe would be, let's just write it here also. Now here what is happening, if E is greater than here, so that means this whole power term is positive and some, so this will be gives you some e to the power something by 0. So that means plus 1. So e to the power something, so e to the power infinite plus 1, right? E to the power infinite plus 1 is gives you also infinite, and 1 by infinite would be simply 0. So F will become equal to 0, right? Now for 3, third case, now let's suppose, like in the problem, if E is equal to F, then what happens equal to F? F will be simply 1 by e to the power, so it would be 0 by kBT. So 0 by kBT basically gives you e to the power 0. E to the power 0 is nothing but, so it gives you basically e to the power 0 plus 1. So e to the power 0 is nothing but 1, right? So it gives you 1 plus 1, so half. So now if you draw the curve, so anyway, the answer is, that means that probability of number of electrons at absolute number equal to 0 when equal to F would be simply half. Okay. Now if you draw the diagram of this thing, Fe as a function of E, right? this would be simply comes like this, right? If this is, let's suppose is EF, this would be comes like this. This is half, this is 1. And this thickness should not be that big, like this. I mean this, let's suppose this deviation, I mean this energy range that it takes from coming from 1 to half and from half to 0 should be very small. Like this thickness should be very small, okay? Because this is happening at t equal to 0 Kelvin. Now if you take t more than Kelvin, more than 0 Kelvin, then it will become like this. The synergy spectrum simply becomes broader. That is what is greater than 0 Kelvin. I mean highest greater than 0 Kelvin. That is half, that is 1, simply same. Okay. So these are basically the possible explanation how like we have solved the problem, like for equal to EF at equal to 0 Kelvin simply gives you probability, simply gives you half. Okay. So now it comes to the problem number 3. So what problem number 3 tells us? When operation of the question, that means question number 2, previous question, either lowered the temperature at which there is 1% probability that are still PB upon the foregoing analysis. Will be occupied by an electron. One PB is 9.6 into 10 to the power minus 9.3. Okay, this is the problem. So the thing is, now the temperature is not 0. Right? That has to be find out, but certainly from the problem it looks like it should not come as 0. But here what is happening? The previously, like here, at the temperature that we need to find out, there is 1% probability that a state with an energy uh, okay, so 1% probability that the particles will be at 0.5 electron volt above the energy Fermi energy level, right? So that means the Fe basically would be 1% at particular energy state, but that is 0.5 volt above the Fermi energy. So that means the energy should raise at certain temperature. Otherwise, anything like any energy state that is above EF at equal to 0 Kelvin, the probability should be, the occupancy probability would be simply 0. But here, as there is 1% probability that a certain number of particles can have the energy state that is 0.5 electron volt higher than the Fermi energy. That means the T would be certainly not 0. And so what would be the value of T that we have to need to find out? So let's first write the distribution Fermi function, Fermi distribution that you already know. Phi equal to by EBT by plus 1. Now here the probability at that particular state would be 0.01%. That particular state is we already discussed, that is 0.5 volt above the Fermi energy. That means, this means E minus EF would be 0.5 electron volt, right? And Kb is the Boltzmann constant. But in this problem, you have to carefully convert this Boltzmann constant that is given in joule to electron volt, right? Joule per Kelvin to electron volt. So if we convert it, kBT will simply become, so previously kBT was 1.38 into 10 to the power minus 23 joule per Kelvin, right? Now we already know that 1 electron volt will be simply equal to 1.6 into 10 to the power minus 19 joule. Now, so that means if we multiply this kV value with 1.6, this gives you 1.6, 1.38 into 10 to the power minus 19 minus 38. This gives a kV value in the electron volt scale. The value would be simply 1.0 10 to the power minus 4 electron volt per Kelvin. So this will be the Boltzmann constant. Now what you have to do? So now the Fermi function would be Fe Fermi function would be simply Fe equal to 1 by B6 T minus EF by kBT plus 1. Okay. Now that you already know, now just have rewrite it also. Now I have to rearrange this whole thing, right? So now for simplification, now E minus EF by kBT, we can write it there 1 by Fe minus 1. This is now if we take log, if we take log on the both side, this it simply gives us E minus EF by KBT into log of 1 by F3 minus 1. If that gives you T equal to E minus EF by AB log of 1 by F3 minus 1. Okay. This just we have done just for simplification of the problem. So now, as we have done the simplification, now what we have to do, we have to just substitute all the values. Okay. So right here, the first Fe is 0.01. So this will gives you 0.5 of Kb already know that is 1.3 into 10 to the power minus 4 minus 4 into log of 1 by 0.01 minus 1 U would be equal to so E minus EF is 0.5, so 0.5 into 1.38 into 10 to the power minus 4 into log of 100 minus 1, so it gives 0.55, 1.38 into 10 to the power minus 4 into log of 99. So it's equal to 0.5 into 1.3 into 10 to the power minus 4. Log of 99 basically gives you 4 point. So value of log of 99 is 4.595. So 4.595. This gives you 0.5 into 6.34 10 to the power minus 4. That gives you 1261 into 1261.8 Kelvin. That is the temperature. 1261.83 Kelvin. So this is the way. Not this is nothing but just everything is given. Just you have to do the from this formula. You have to basically calculate the T. Because the probability E minus EF is given. So at what temperature that particular state will be having particle with a probability of 1%. For that, you have to, there should be a value of T, that value of T you have to calculate. So we have done some rearrangement of the terms into this equation to get the whole expression which is independent of T, because we have to find the value of T. So here is the expression T equal to this. From there we just substitute the values and we got the temperature, that is 1261.83. Anyway, so this I forgot to write the options here. So certainly the options are, one option is the option that we have got, that is the first option. Option B was 1295.83. So C is 1361.25 and option D is 800.361. So we got the option A as a correct answer. So I hope all of you understood how to solve this problem. Okay. So so now this problem is done. Okay. Now we'll go to our next problem. That is the problem number 4. Okay, so problem number 4, let me write the question first. So problem number 4 asks that in which options all are bosons. Option is electron, proton, nucleus, or which nucleus of sodium and nucleus of oxygen. Option B is proton, nucleus of sodium, of hydrogen, nucleus of oxygen. Option C is proton, nucleus of sodium, nucleus of oxygen. Option D is photon, not proton. Photon, nucleus of sodium, nucleus of oxygen. So these are the 4 options are given. Okay, so in which case all the options are bosons also. So you have to check basically. So let me first write down the properties. So what are basically bosons? These are, we said it, particles with integer spin, that is 0, 1, 2. This consists, so these are not fermions that has plus half, 3/2, 5/2 spin. And for composite particles, like here, like sodium or oxygen, like this nuclei. So like nuclei and the bosons or fermions depending on the number of nuclei, that means protons plus neutrons they contain if they contain even number of nucleons, then they are bosons. Okay. If they contain odd number of nucleons, then they are basically fermions. Okay. So these are the two types of particles here, for example. So now bosons, fermions are there. Now analyzing the nuclei. So let's take all the things. Okay. So for fundamental particles like photon, electron, proton. So like there the options also like photon, proton, all these things, electrons, all these things are given. So photon is basically fundamental particles. These are basically not composite particles fundamentally. So basically you cannot basically like divide the particles into more like number of particles. This is just one single particle like this. So fundamental particles. Proton. Proton is a boson. Proton is a boson. Electron. Electron is a fermion. And proton is also fermion. Okay. So electron, proton both have integer value of spins. That's why they are basically fermions. And photon is a boson. So this has a spin of one for photon. This has spin half. This also has spin half. Electron and proton. So now let's take for option 1. Option 1, as you can see in there is this electron is already there. So don't need to check the other accounts because electrons makes this whole series. Not all are bosons. It makes this series that all the other nuclei are not visible. The correct answer. Now in the next answer, photon is there. Sodium is there. So let's check sodium. Nucleus of sodium. So sodium and also deuterium and oxygen is there. So let's check all these things. All these given options. Okay, whether they are photon or like bosons or fermions. Okay. So let's check for sodium first. So let's check from deuterium, that is 2H2 first. Okay. That has basically 1 proton plus 1 neutron, right? That means 2 nucleons. 2 nucleons, that means it's a even number. So that means a boson. It's a boson. Now similarly, 11 sodium 22, that has 11 protons and 22 minus 11, that would be the number of neutrons. That basically gives you 11 proton plus 11 neutron gives you 22 nucleons. Okay. It's also even. This means it's a boson. It's a boson. Now the third one is oxygen, right? So oxygen, first one is oxygen. So there are two oxygens are given. As you can see in the other on other option 17 OH also given, 18 OH also given. So let's consider both the oxygens. So first take 17 OH, which has 8 proton plus 70 minus 8 electrons. This gives us 8 plus 9 equal to 17 electrons, and 1808 is gives us 8 proton plus 18 minus 8 neutron, that gives us 8 plus 10, that means 18 nucleons. So this first one has odd number of uh, nucleons, right? So basically this means it's a fermion. And next case, as it has an even number of nucleons, so it's a boson. So I hope all of you understood how we will solve this problem. So now the thing is, now from the answer we have taken out what are the possible correct answers. So from the answer it looks like that if this is discarded because 17 is a fermion, so option D is discarded. Option C, proton, neutron. So proton is a fermion. This is also excluded. But this is, I guess, photon is a boson. Nucleon. This is also boson. This is also boson. This is also. So option B is the correct option, right? So option B is the correct option. Photon, nucleus of sodium, nucleus of deuterium, and nucleus of 18 oxygen. Okay, oxygen 18. So that's it. The problem number 4. Okay. So basically, the main concept is here, like for fundamental particles, like photon is a boson, but other particles, electron, proton, these are the formula that you should know. And if it's a composite particle like nuclear, like according to the problem, the sodium or the oxygen or the deuterium, so this kind of particle is there, then you have to calculate the number of nucleons. If there is even number of nucleons are there, that means that composite, that in particular nuclear would be a boson, and if there is odd number of nucleons, then that nuclear would be simply a fermion. So for composite particle, this is the way to calculate whether they are boson or fermions. Fundamental particle you have to remember from the spin values, and that's it. Okay. So now we go to the fifth problem. So the problem number 5. So problem number 5 is done. Problem number 5 now we'll try to solve it. So let's see what we first. So let me just write the problem first. So can see the uh, gas made up of two identical particles. Okay. Suppose that suppose that each particle can be in one of the four possible states, quantum states. Okay. Quantum states in case of safety statistics. What will be the probability of having both particles in the same state? Okay. Option A was 1 by 8, B was 1, C was 0, D was 4. Okay. So now it's the same kind of problem. The first problem of this. Similarly here, gas. Now in this case, what the minimum there is, and each particle can be one of the four possible quantum states. So previously it was 3, I guess, and now it's 4. And in case of FD statistics, what will be the probability of having both the particles in the same state? So the thing is, here also it follows the FD stat. So we have already discussed, right? So let me write it one second here also. The answer is the particles follows FD statistics. This means probably exclusion principle applies, which means identical particles cannot occupy the same energy state, right? So here, according to the problem, there are 4 energy states are there, right? Having the equal value of energy, 4 possible quantum states are there with different energies, right? So the probability of having both the particles in the same state will be simply 0, right? So that means that the probability of having both particles in the same state is basically 0. So that means the correct option will be option C. Okay. So I hope all of you understood the question 5. Now, so now, so question number 5 is done. Now we move to the question number 6. Question number 6. So question number 6 now. So question number 6 is Fermi function Fe. Basically, it is given by 1 by, okay, here the expression is a bit different, minus A by K beta plus 5, okay, gives the probability of occupation of electron per energy state, then the probability of number of electrons at absolute temperature T equal to 0 Kelvin when equal to EF is, option A is half, option B is 1, option C is 0, and option D is 1 by 6. Okay. So the thing is, the Fermi energy function is given. So this is the probability. Here the expression is slightly different. There is a plus 5 factors instead of plus 1. Anyway, gives the probability of occupation of electron for energy state that you already know. So in this case, the probability you have to calculate at an absolute is equal to A. Okay. The same type of problem I did earlier also. So, but now here the thing is a bit different. So anyway, so okay, so what we can do first, so let's first write the expressions and everything. So this is the basically the expression. If E equal to 1 by E by E to the minus EF by KT plus 5, this gives us the probability of occupying the state E at temperature T probability of occupying the state at temperature T. Uh, EF is the Fermi energy here. Okay. So now the thing is, here the expression is slightly different, but at the same time to calculate what is the probability at equal to 0 and when equal to EF. So now, uh, so when, so this is the factor, right? E minus EF by KV. So this thing will become minus infinity. You see, write it here. This it simply becomes, if T is here 0, right? T is 0. So if in this case, if E is greater than EF, that simply gives you, if first x E is greater than EF, this simply gives you this term as plus infinite, right? Right. If E is greater than EF, this gives you plus infinite. Okay. If E is equal to EF, that gives you 0. And if E is less than EF, that gives you minus infinite, right? Now if you substitute these things here, so if that means if E is greater than EF, as you can see from this problem, so Fe, that is basically 1 by e to the power e minus EF by ABT plus 5. Okay. So for the case E greater than EF, so for this case, this expression should become, so this would be simply becomes 1 by e to the power e minus EF. For E greater than EF, we have discussed that will become plus infinity, right? So plus infinite plus 5. This is simply gives 1 by infinite equal to 0. Similarly, for E less than EF, if you would be simply 1 by e to the power minus infinite, right? Plus 5, that gives you 1 by infinite plus 5, that gives you 1 by 0 plus 5, 1 by 5. So that is the case for 1, 2. Now the case 3, when E will be equal to EF. So for that case, if E would be simply 1 by e to the power EF minus EF, that gives you 0. 0 by ABT plus 5, this gives you 1 by e to the power 0 plus 5. So e to the power 1 plus 5, 1 plus 6. If E, it simply gives you 1 plus 6. Okay, that is the case where E equal to E. So that's how we got different terms, right? For the case E greater than EF, is smaller than EF and equal to E. 1 by 6, 1 by 5 and 0. Okay, so for this problem the correct answer would be, that means 1 by 6, right? 1 by 6. So I hope all of you understood how to solve this problem. So uh, here the main thing is this distribution function is actually a bit different from the actual Fermi-Dirac distribution function. So here F is basically equal to 1 by e to the power e minus Ef by kBt plus 5. So that actually make the problem a bit different. And so first what I have did, so for different cases, uh, we have calculated the E by E minus Ef by kBt. So for E greater than Ef, E minus Ef by kBt simply gives you plus infinity. For E equal to Ef, for this case 0 by kBt, this gives you 0, and if E less than Ef, this gives you minus infinite. Okay. So now for the whole three cases, you substitute this factor into this expression, probability distribution function. What you got if you substitute the expression? So Ap would gives you 1 by e to the power infinite plus 5. So infinite plus 5 gives you infinite itself. So 1 by infinite gives you 0. Next thing, when e equal e less than Ef, in that case we know this factor becomes minus infinite. So that means e to the power minus infinite plus 5. 1 by infinite gives you basically 0. So 0 plus 5 is 5. So 1 by 5. Last is if e equal to Ef. For that case, if e equal to Ef, so Ef cancels. So that gives you 1 by e to the power 0 by kBt. So e to the power 0 by kBt gives you e to the power 0. E to the power 0 is nothing but 1. So 1 plus 5 is 6. So the probability gives you 1 by 6. But in the problem, you have to find out for the case e to the power Ef, that gives you 1 by 6. And also you can, if you want, you can also draw, right, the energy level just like the previous one. Here also, Ef as a function of E, you can draw it. So this is the Ef. Let me draw a bit closer. So let's suppose this is the Ef. Now this will be simply this. This would be 1 by 5 and this would be 1 by 6, right? Okay. This is how you should solve the problem. So now now so now comes the problem number 6. Okay, the last problem. Okay. Okay, so problem number 6 is done. Okay, so it's done. So that means the whole tutorial is done. Now still we got like around half an hour left. So what we can do, we can solve some extra problems which is not from the tutorial. Okay. So we will try to solve like this type of problem, some problems. Okay. So okay, similar types of problem. let's take the first problem 1. So, side, so some extra problems. Extra. So problem number 1 is the Fermi energy of a metal at T equal to 300 Kelvin is 5.0 electron volt. Okay. Now what you have to find out, calculate the probability that state 0.1 electron volt below the Fermi energy is occupied by an electron at this temperature. So basically the Fermi energy value is here given. I believe that 500 kilojoules is 5 electron volt. Now we have to calculate at this temperature what is the probability of the electrons that occupies the state that is 0.1 electron below the Fermi level. So in that case, first write AF is the energy or the probability function, that is the, as this is Jack formula, so E minus EF by KBT plus 1. Okay. Now here E is EF minus 0.1, that gives us 5.0 minus 0.1, that gives us 4.9 electron volt. Because EF is 5.0, right? 5.0 EF. And EF is already there. I think in the problem it's limited. T is 300 Kelvin. Now Boltzmann constant we have already calculated, right? That in electron volt before. That was like in kV, simply 8.617. That we have calculated already, right? Now what we just substitute the value. So first let's calculate E minus EF by KBT. So exponent. So exponent is the E minus EF by KBT is 4.9 minus 5.0 is 8.617 minus 5 into 300 will basically gives you minus 0.1 equal to 0.05 851 gives you around 3.87. Now in the Fourier function the substitute if you be simply 1 by 3 minus to the power minus 3.87 plus 1 would be leaves you to the power 8.7 is nothing but 0.0206 plus 1. This gives you 1 by 1.0206, gives you around 0.98. That is the Fermi energy function. Okay. So that's it. Okay. So simply normal numerical problem. Okay. So Fermi energy function is already given. Now at a particular temperature, you have to find a probability that the electrons would be having, and that state is basically 0.1 electron volt below the Fermi state, 35 electron volt. So in that probability distribution function, just substitute all the numerical values. E minus E is 4.950. K bit you have to write in terms of the electron volt. Temperature is given 300 Kelvin. And from there, first you calculate the exponent, and from that exponent you have substitute in the expression of the probability function, and from there we get the probability as 0.9. Okay. Now the next question, let's calculate the problem number 2. So problem number 2. Equal to 0 Kelvin. The Fermi function predicts sharp occupancy of states for T equal to 0 Kelvin. Calculate the temperature at which the probability of a state above EF equal to 6.0 Indian is 10%. So in the problem, it's given that we already know that at T equal to 0 Kelvin, the Fermi function predicts a sharp occupancy of state. That means that we know that at Fermi energy there is a sharp peak, right? So that like suddenly that Fermi function drops from 1 to 0. Like at particular equal to F, that is 0.5, but after that equal to F, that Fermi function abruptly goes to 0. Okay. So that's mentioned in that first line. Now the main problem is for T equal to 0 Kelvin, calculate the temperature at which the probability of a state 0.2 electron volt above the energy state equal to U into 6 electrons is 10%. So now previous problem we have calculated the uh, probability. Now for this problem probability is given 10%, but we have to calculate the temperature, right? So first write the Fermi function here first. So if is nothing but 1 by e to the power e minus ef by kBt plus 1. Okay, now here the probability is given, that is 0, that is 10%, or 10 means 0.1, right? 0.1 probability. I mean the percentage, if you convert it into the probability, that means 10% is 10 by 100, that gives you 0.1 as a probability. So now, and E minus EF is what? So 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 let's first E minus EF. So E minus EF is nothing but 0.2 electron volt, right? Because we have to calculate the probability 0.2 electron below the Fermi energy levels. E minus EF will be simply 0.2 electron volt. KB we already calculated. For this also we need in terms of electron volt, that we have previously calculated. That is this one. Now, so okay, so now everything comes to like this. Probability is okay, so probability is 10%. Okay, so now just write this thing. So if we is so we can write this thing as this, right? To the power e minus ef by kBt plus 1 equal to 1 by fe. That's is to the power e minus ef by kBt gives you 1 by fe minus 1. Then if you take the natural log both sides, e minus ef kBt gives you log of 1 by 18 minus 1, so this gives you E as log of 1 by Fe is already know 0.1 minus 1, and that is going to be E minus Ef is already, you know, that is 0.2 by kBt. So everything is there, so just 0.2 by kBt is log of 10 minus 1 is log of 9. So log of 9 is 0.2 by kBt is 0.197. So T would be simply 0.2 by 2.197 into 8.617 into 10 to the power minus 5, right? This simply gives you 0.2 by 1.89 minus 4. So T gives you 1057 Kelvin. Okay, that's the temperature. That's the temperature at which the probability of occupying the state 0.2 electron volt above the Fermi energy would be 10%. This is the correct answer for this problem. Okay. Now I've done the second problem. This is a quite not that much difficult problem. Now we goes to the next problem. It's a different types of problem, different kind of problem. So problem 4. Question is, given the density of states dE proportional to e to the power half derive and x expression for the total number of electrons in the conduction and using the Fermi distribution at equal to 0 Kelvin. Okay, find out. So question is, the density of states is given electron for a particular energy state that is proportional e to the power half. Now what I have to do, from that density T, we have to calculate the total number of electron at that particular state convection using the Fermi distribution equal to 0. So now T equal to 0, that's a very important thing. Okay, so that means the distribution above the Fermi energy will be simply 0. So that means that our integration limit also should be between 0 to 11. So let me write it again for much more clearer understanding. So the Fermi distribution Fe would be 1 by e to the power e minus ef by kBT plus 1. This is the distribution. Now at T equal to 0 Kelvin, what happens? Fe is equal to 1 for E less than F and 0 if E is greater than F. Now here EF is the Fermi formula. EF is Fermi energy. So now, because in the problem itself it's mentioned that for hard temperature, that is more than 0 Kelvin, you have to calculate distance. So now, as these are given, so now you have to first the total number of electrons. So now at a given state, if at a given energy level E, if the density of energy is given, that is also in terms of energy it's given, density of density of states in terms of energy is given, then from the, and also the probability distribution function of the particles, that means the probability of occupation of the particles, fraction of the particles that can exist in that particular energy state, that is also given, that distribution is already given in terms of energy. You can calculate, I mean, by using both these two quantities, you can easily calculate the total number of particles. Okay. In this case, the particle is electron, so that you can calculate. So the total number of electron n is given by n is simply the integration to 0 to infinite limit. D is the density of state, F is the probability of occupation, and D is the small energy interval. This would be simply total number of electrons at that particular energy state E. So now what you have to do, so now at t equal to 0 case, at t equal to 0 case, as you can see here, at t equal to 0 case, for energies higher than EF, the F simply becomes 0. Right. So there is a upper integration limit. Okay. That limit is nothing but the EF. Because if you exceed EF, the distribution is becomes 0. So this whole thing will become 0. So the integration upper limit would be EF. That would gives you dE by del E. So now dE is already know, the expression of dE is some proportional to e to the power half. So you can take C as a proportionality constant. So now if you substitute this thing here, this basically gives us the total number of particles. Here is electron. It's nothing but 0 to EF C e to the power half dE. That gives you n equal to C e to the power half d. C is basically constant, so you can take it outside, and this gives you 2 by 3 C e to the power 3 by 2 from EF to 0. That gives you 2 by 3 C EF 3 by 2. So the expression of the total number of particles will be given by this expression only. So I hope all of you understood how to solve this problem. So basically the density of energy state is given. Now from there you have to calculate the total number of electrons. The electrons. Okay. So as electrons we know follow the Fermi-Dirac statistics. So first we write the expression of the Fermi-Dirac statistics for in case of electron. In case of any fermions. Now from there, this is basically the formula of calculating the total number of particles at that particular energy state, density of states into the probability of occupation into the small energy level G. That this gives us the density of number of particles at a particular energy level E, and between E and E plus del E. And if you integrate it from 0 to infinity, gives us the total number of particles. But in our case at t, this thing is happening at t equal to 0. The upper limit would be simply EF, that is the Fermi energy level, because if we exceed the Fermi energy level, the probability of occupation simply becomes 0. So now having the limits, now if you substitute the density of states, and if you do the integration, this gives you the total number of particles. Okay, that is this thing. So now the problem number 4 is done. Now we goes to the problem number 5. Okay. Now problem number 5 is slightly different. It's similar to the problem number sorry, maybe problem number 4, but slightly different. So 5 is for an electron gas at t equal to 0 Kelvin. Calculate the number density of electrons in given one effective mass m star to forming energy EF3 times constant. Which these three things are given basically. You have to calculate the number of density in terms of these three things. We already know that at t equal to 0, the number of particles at a particular state E is given by the n integration. No, that is that you discussed there. Now let's write it at t equal to 0. Previously, you have calculated the total number of electrons, but now you have to be careful because now you have to calculate the density of electrons, not the total number of electrons. Okay. So for density electrons, the formula will be slightly different. The total density means the total number of electron per unit volume, right? That gives you the density. Per unit volume is given by n equal to 0 to F dE by dE. So this basically is the density of particles, not the total number of. If there is total number of particles, then you have to multiply this d is also with Fe, right? So now one expression that you have to use. I am not doing the derivation because this derivation takes a lot of time. But in any book you would find it. The density of electron at a particular state E in a 3D for a 3D free electron gas would be simply 2m star 3 by 2 2 pi square h cut q into e to the power half. This is nothing but the density of states in 3D for a free electron gas. Okay. Here m star is the effective mass that we have told you, right? M star is the effective mass. Okay. So these things are given. So now is energy. So first thing first is the D. So D is this. So if you calculate the total energy, total number density, that is basically the N. N is simply 0 to EF 2m star 3 by 2 into u pi square h plus q e to the power half d. Now this whole thing you can consider it as a constant. You can just take it out from the integration, right? That gives us n equal to 2m star equal to the power 3 by 2 pi to pi square h squared q 0 to EF e to the power half g. Now, if you do the integration e to the power half e, that simply gives you 2m star 3 by 2 pi square h squared q. This gives you e by 3 e to the power half, sorry, e to the power 3 by 2, and the integration limit will be 0 to a. Now if you substitute all of this, it still gives you 2m star e to the power 3 by 2 2 pi square h squared 0. So this would be the number density. So this is it. This is the expression, number density expression, which is this. And according to the problem, this exists all these things like m star, that is the effective mass, the EF. This is EF. This is EF h squared. So all of the terms are there into the expression as it's mentioned in the problem. So how do we do that? So unlike previous problem, here we have to calculate the number density, not a total number of electrons. So this is the formula of the number density, and the D, the density of states. So in order to calculate a number density, we only need a density of states. And for a 3D electron gas, the density of state is given by this formula. So we just substitute this thing here and do the integration as it's happening at t equal to 0 Kelvin. So the integration limit should be from 0 to EF, right? That we are doing it right now, 0 to EF. Now if you do the integration, that basically gives you 2 by 3 to the 3 by 2, the integration 0 to EF. Now if you put it, the limit, the total energy density will be given by this. That's how you basically have to solve the problem. So that's it. This is our final problem. So we have almost come to the end. So in this tutorial session, we mostly discuss about different types of statistics in classical and quantum mechanics that we are using. One is the Maxwell-Boltzmann statistics, or the MB-stat. Another two, that is mostly applicable for classical particles. Another two are basically the Bose-Einstein statistic, that is the bosonic particles, where the particles, like more than one particles, can occupy a singular state. But other one is also for Fermi-Dirac distribution, that is also for quantum particles, indistinguishable particles. And but in that case, more than one particle cannot occupy a single energy state. But that means the Fermi states basically obeys, the fermion basically obeys the Pauli's exclusion principle. And how do you recognize between a boson and fermion? The fermion has integer spin values, that means like half 3 by 2 like this. Basically half integer spin values, and for bosons just normal integer spin values. So, and bosons obviously obeys the Bose-Einstein statistics. So, and these three types of statistics has their own different types of distribution function that we have discussed in well advance. Okay, in the first problem itself. So these are the distribution functions are given. So now using this distribution function, like we have calculated different quantities like probability distribution, the temperature, everything. Many types of things I've calculated. Okay, so that's it. All of you understood. So let me just end the meeting.